In this example, we're going to have another look at the motion of gravity acting on an object and some help to problem solve questions like this. So the question says a ball is dropped from a height of 30 meters above the ground. 2 seconds later, another ball is thrown upwards from the ground with a speed of 5 meters per second. They collide at time t after the first ball was dropped. So find t, right? In other words, the time when these two balls collide. And part B is going to ask us at what height above the ground these two objects collide. So we can already start thinking in terms of where this is going, right? Now, because these objects are two separate events, we need to equate them using the same starting and direction, otherwise we can't compare them, right? So if we consider that we want to at some point find the height above the ground, well, we could very easily make the ground our starting location, and then the object's displacement would be its height above the ground. And in our case, we will set the direction as above the ground being positive. That tells us that ball number 1 started at a positive 30 meters displacement, which makes sense, it's 30 meters above the ground. And ball 2 has a displacement of 0 because it's on the ground, the ground being our starting position. Now, because these two objects are separate, we need to look at and create for ourselves two displacement time functions for each object. So let's have a look at the information that we're given for ball number 1, right? The mass of the object is unknown, right? And so we will just give it a mass m1 for now. We know that the initial velocity is equal to 0. We don't know the displacement or the time. That's what we want to find out, right? We don't know the final velocity, and we don't know the acceleration. So there are many things missing from this puzzle. So the first thing we're going to do is consider the forces, because that will help us find the acceleration. Now, the only force that we can consider in this example is the gravitational force, right? We aren't given any air resistance forces, and there are no other forces that are mentioned acting on this object. So the only force we have is the force due to gravity, right? And we know that the force exerted by an object on gravity is just mass times the gravitational constant. In my example, I don't know the mass. We've called it m1 times g newtons. Now, usually this would present ourselves with a problem. If we had other forces involved, we would have to know the mass of the object in order to work out the acceleration, right? But because we are only considering the gravitational force, we can actually assume that the acceleration is the gravitational constant. And we can easily prove this by saying force is equal to mass times acceleration. This is the net force, right? And in our case, we only have one force. Remember, this is a negative force because it's acting in the opposite direction to what we have called positive. So we have minus mass of 1 times g as the force, equal to the mass of the object, which is just m1. And we are trying to work out the acceleration. We can see this is just going to cross-cancel these m's, and I'm going to be left with the acceleration is equal to minus g. So my acceleration is equal to minus g, which is just minus 10 meters per second squared. At this point, I have enough information to create my first displacement time function. Okay? So we want displacement and time as a function, and we have initial velocity and acceleration. So the equation we will use is displacement equal to ut plus a half at squared. Now, we also need to remember that we have a starting displacement, okay, which we need to take into consideration. So the displacement for my first function, I'm going to very appropriately call displacement 1, because this is for the first ball, is equal to u. So u is equal to 0 The time will be time 1, because this is object 1, plus a half. Acceleration is minus 10, and t1 squared. That finally gives me displacement equal to 0 plus 5. Well, that's going to become a minus 5t squared. Right? Now, this would take the displacement for time if the object was on the ground, except our object is not on the ground. It has a starting displacement of 0. So s of 0 is 50. In other words, the intercept is 30 meters. Okay, and I will do a video on I'll include some transformations to show you exactly why this is. Okay, so we have our displacement equal to the 30, which is my starting displacement, minus 5t squared. Okay, time 1. That's my displacement for ball number 1. Right, ball number 2, we need to do another force diagram, and we will need to also consider all the information that we're given for ball 2 as well. So we know that the mass for ball 2 is unknown, so we'll call it m2, and as you saw in the first example, it made no difference. All right, it could be the same, it could be a different weight, we don't know. And based on that, we can make the same assumption that the acceleration is going to be the same, okay? And because the acceleration is acting in the same direction, we can say acceleration for ball number 2 is also going to be minus 10 meters per second. We know the initial velocity is equal to 0. We don't know the displacement, and we want a time function. Right, we now need to consider the time, okay, the time that this event happened. Now, if we go back to our diagram when we have a look at the ball, we know that if we consider the displacement and velocity of ball number 2 in relation to ball number 1, the displacement for ball number 2 will remain at 0, right, for 2 seconds, right, because it was only thrown 2 seconds after. And so we can say that time for this one is going to be t minus 2. Right, so time 2 is equal to t minus 2. So whatever the starting in time is, minus 2. And again, I will do a transformation video for you guys and explain to you, and you can see visually why this happens. Right, the only thing we have left to do now is create our displacement function. So we'll call displacement, we'll use the same formula again. This is displacement 2. It's equal to, well, we can see we're going to get 0. I think I'm talking porcupines, aren't I? We can actually go back to the question, and the question said our starting velocity was 5 meters per second. So we have 5 for our initial velocity. Our time, remember, is now t minus 2 plus a half. Acceleration is negative 10. And we have t minus 2 squared. This gives me a displacement function of 5 t minus 2 minus 5 t minus 2 squared. Right, so now I have 2 displacement functions, right? Their times are comparable, right? We've taken into account that ball number 2 only starts 2 seconds after ball number 1, and the only difference now would be their displacements. Okay, their displacements will not be the same for any given point in time, right? So for instance, at t of 0, they will be 30 meters apart, and as the time increases, their displacement will slowly become the same. So in other words, if we want to find the time when these two objects collide, that is the time at which both their displacements are equal to each other. So we have two displacement functions, S1 and S2, and we can say that at the point of contact, well, their displacements must be the same. So we can even state at collision, S1 must equal S2. Right, so let's make our two displacement functions equal to each other. So we have 30 minus 5t squared equal to 5t minus 2 minus 5t minus 2 squared. It's just a matter of expanding things out, right, and solving for t. So I'm going to do this all in one step. I'm going to think about the expansion and just multiply everything by 5. So I'm going to get minus 5t squared. Inside the bracket, I'm going to get minus 2t times 2. So that'll be minus 4 times 5, which is plus 20t. I'm going to get minus 2 squared, which is 4 times minus 5, which is minus 20. Right, I can already see that these are going to cancel out. I'd like my t's to be positive, so I'm going to keep them on the positive side. So they will be 25t over here. I'll move all the constants over to the other side. So I'll get minus 30. I need to add, so this will be equal to 60. And so I will get t equal to 2.4 seconds. So at 2.4 seconds, these objects will collide. Now, we need to find the height, right? And we can find the height using either one of our two displacement functions, okay? Either because they happen at the same time, right? We have a choice, and usually the best thing is to use the easier one, right? And in our case, this is going to be 30 minus 5t squared. It's just the easier one. 2.4 squared, and this is going to give me 1.2 meters. So they collide 1.2 meters above the ground. So again, just an overview. We first drew a little representation in the corner over there to explain to ourselves where the starting and which direction is positive. This is very important when we're dealing with forces and motion, right? Then we considered the forces acting on the object to find the acceleration. And once we did that, we created two displacement time functions in order to solve a combined simultaneous equation.